In this video, we're going to be giving just a quick overview of the main regions of a titration curve between a weak base that's being titrated with a strong acid. So similar to our weak acid titration curve, the first initial point on your curve is your initial pH, except in this case, it's going to be a weak base pH calculation. So you're still going to use an ice table, just like you normally would to figure out the pH of a weak base. Just remember that initial concentration that you get is going to be in terms of hydroxide, so you have to be careful. So what I mean by that is if we have our base, which I'm just signifying with B for right now, plus water, is going to act as a base, accept the proton from water to make its conjugate, and then produce hydroxide. And then that concentration of hydroxide would help you to determine the initial pH. All right, if you look at halfway to the equivalence point, that also exists on a weak base strong acid titration curve. So here's my half equivalence point. Okay, and if you think about the reaction that's happening between the base and the strong acid, and the weak base and the strong acid, where that proton's being donated, you're forming its conjugate. So we're looking at really the concentration of the weak base that's still remaining in solution versus its conjugate that's been getting produced as it reacts with its strong base. So when we think about what the half equivalence point is, we're really talking about the concentration of the weak base being equal to the concentration of its conjugate at that point. Now keep in mind with the half equivalence point though, we're still in pH, which is in terms of the concentration of hydronium. So at this point, the pH is equal to the pKa. Okay, usually when we're dealing with a weak base, we're interested in the pKb. So you would have to do one additional step of doing 14 minus the pKa that you would determine from the half equivalence point. So just be aware of that. In that buffer region, which is about plus or minus 1 pH, that would be your Henderson-Hasselbalch equation that you're using to figure out the pH. This is before you reach the equivalence point. So this is your buffer region. This is where you would use your Henderson-Hasselbalch. Okay, based on that weak base and its conjugate's concentration. All right, moving on to the equivalence point, which is already labeled for you. This is the point where you're looking at, if we go back to the original equation, you have your weak base and your strong acid. Those have been completely consumed. So at the equivalence point, it's really about the conjugate acid of the weak base and seeing basically it as a salt. So you're doing a hydrolysis of a salt. Salt here, with our salt being the conjugate acid of that weak base. When that reacts with water, okay, it's going to act as an acid, reproducing the base, and then most importantly, producing hydronium. Now the other thing with hydrolysis of a weak salt is that you're involving a weak base and a strong acid. So this production of hydronium is supporting the fact that it's not just hydrolysis of a salt, but you should be thinking about the hydrolysis of an acidic salt that's going to produce hydronium. So this equivalence point should be at a pH that is less than 7. That's one way to kind of identify that you have a weak base being titrated with a strong acid, is you're going to see that pH less than 7 because of the acidic salt. So you'll go through a salt calculation at that point. Just like in the other one, when you get past the equivalence point, it's going to be excess of the strong, in this case, acid. So here, after your equivalence point, you are going to have excess strong acid here. So you need to find your excess hydronium. Okay, making sure you divide by the total volume there in order to find your pH. Okay, so those are again just the general regions, and we're going to be working on the calculations for each one of them in the next video.